Well, our next speaker in the session is Shahin, Sheikh-Jabbari, getting a coherent arrow of time. Well,
Thank you for having me here, and I would like to thank the organizers for putting this memorial session. I first met Durmuş in 1999 when I was a postdoc at ICTP. His office was in front of me, and we had discussions for the next 2 years every day. And then we had several encounters, both in Izmir and elsewhere. And he visited us at IPM. It's a great loss. So he was a very good friend. He was sort of a man of integrity in science. And I hope that the younger people here would try to follow him in this path. I'm going to tell you about something which, if Durmuş was here, I'm sure he was very excited to hear about. The problem is a bit different than what the three seminars that you have here so far. It's about the question of arrow of time in physics. So I'm sure everybody has heard about this problem. And basically, it has been one of the main questions in physics in the last century or so. It has not found a satisfactory answer yet, and I'm going to give you a proposal which is based on general relativity and specific way to basically quantize the theory. The question of arrow of time is basically very basic and very simple one to state. The point is around us, wherever we look at, here in different length scales, from the far galaxies up to even atoms and so on, we see that time is flowing in the same direction. It's going from past to future. It's so obvious for us that we never think about this. So, but the problem is you can say, okay, this has been chosen that the time is always flowing from past to future. That's what time is. But the point is, when you look at your basic formulations of physics, like starting from classical mechanics and, thank you, classical mechanics and Newtonian dynamics, there is no specific time direction in Newton's equations. So you have F equals ma, and it's second derivative of time. So if you change the time to minus itself, it just remains the same, the equation. Starting from Newtonian mechanics, you can come to, for example, quantum mechanics. The Schrödinger equation has no preferred direction of time. In relativity, we have special or general relativity. There is no preferred direction of time either. So in all basics formulations of physics, there is no preferred direction of time. So you can say, okay, basically the direction of time comes from the initial conditions. So you have the basic formulation is some differential equations in time. There is no preferred time direction in those basic equations, but the initial conditions may dictate that the time should flow from past to future. So there are a lot of reading material. You can basically find it here in these references. I'm sure the slides will be given there. So there are, this is, so a built-in feature by initial conditions. This is one idea. The other is that it's an emergent phenomenon that we see this arrow of time. But whatever it is, it seems that it's observationally confirmed that there is an arrow of time. So basically in three different formulations of physics, we have encountered three different arrows of time. One is in thermodynamics, which is basically the arrow of time is coming from the second law of thermodynamics, or I can just view it oppositely, that second law of thermodynamics is basically a statement of the arrow of time. So here in thermodynamics formulation, basically arrow of time is supposedly some thermodynamic effect which appears only in thermodynamic limit when we have a large system. That is basically encoded in the notion of entropy. The second arrow of time, which is probably different than this one, is cosmological arrow of time, that all the universe that we see around us, for all of them, very distant galaxies to here and everywhere that you look at in the universe, time is flowing in the same direction. So in the thermodynamic arrow of time, there is no reason why, for example, the thermodynamic systems that we have here should be exactly the same as the thermodynamic systems in far distant galaxies. So the cosmological arrow of time is probably not related, at least at the level of basic physics that we understand, to the thermodynamic arrow of time. But apparently they are working in the same direction. So the same thermodynamic systems that we see here, we can see on the sun, we can see on the distant galaxies. And so although there is no relation between them, they seem to be flowing time in the same direction. Then there is a third one, which is even more mysterious, and that's the quantum arrow of time. I told you that Schrödinger equation has no preferred arrow of time. That's fine. But in quantum mechanics, when we do any measurement, there is a reduction of wave function. And that reduction of wave function is, of course, a very mysterious part of quantum mechanics. It's not described by a unitary evolution. But whatever it is, it defines an arrow of time. So whenever you do any experiment, in any measurement in quantum mechanics, all the wave functions reduce to the same direction. Basically, they reduce to some eigenstate of the measurement apparatus. So we have these three different arrows of time in physics that we know as of today. For thermodynamic systems, I told you that this is probably the same as the second law of thermodynamics. If you understood that from basic physics, then you can understand this arrow of time the same way. Cosmological arrow of time has been discussed again in the last 40, 50 years. That the main proposal is that it's basically an initial choice, presumably at the Big Bang time, that has induced this arrow of time that we see. But this idea has been questioned by many people. For example, you can see this one. And the quantum arrow of time is still a big mystery. So we don't have any even sort of good ideas how to describe it. One of the big questions, besides the fact that where does this arrows of time in either of these three cases come from, is that why are all pointing to the same direction? Even if you had individually understood where these arrows of time come from, the very fact that they are pointing to the same direction is still a big mystery. So this is a different question. Okay, so you can see this is basically some ideas which have been around in the last 40, 50 years or more, how to basically connect these different arrows of time. And for example, in the context of, as I said, maybe the best understood one is the thermodynamic arrow of time. For the case of whenever we have black holes, and we have the second law of generalized second law of black hole thermodynamics, and maybe this could be sort of a way to connect the cosmological arrow of time to the thermodynamical one, but still these are just words. One needs to put them into equations. And at any rate, this is a big question, and I would like to basically give you some proposal how to do it, how to find an arrow of time. So my proposal would be based on a very simple idea of how to quantize general relativity. It will be very basic. You don't need to know many details of general relativity or quantization either. So basically, I'll take you through this very simple example. First, I'll discuss the ADM decomposition, which I'm sure most of you are familiar with. Whomever who has had a course in GR has seen this. And the main catch or the main idea is basically how to quantize a system which has some constraints. This is one example of that. And that's what I've called sandwich quantization. And I'll show you how the proposal works and I'll conclude. So this is the proposal. In the ADM decomposition in GR, basically the idea is that we try to separate time and space. This is why it's called 3+1 decomposition. And then it gives you a framework that has been used for over 50 years to sort of quantize GR. But I'm telling you something, I'm putting something new on the table for this procedure, and that's going to give me an arrow of time. So this is the basic, a very quick review of ADM decomposition. As you know, in this, the formulation of general relativity, we deal with space-time metric. Here I'm working in 4 dimensions, 3 space direction and 1 time direction. And because of the diffeomorphism invariance of the theory, you can always write the metric in this form. You can separate time and space, xi, in this way. This is the most general way that you can write any metric, any 4-dimensional metric. But the point is that because of the diffeomorphism invariance, this n and ni, which has appeared here, are not dynamical variables. So they are just constraints. They are manifestations of the diffeomorphism invariance of the theory. If you can choose them, n and ni, for different observers, so different observers would use different n and ni, but they are not dynamical variables. This is like for those of you who are familiar with gauge theories, these are gauge degrees of freedom. So these are gauge degrees of freedom, and it's a choice of observer. And when you write Einstein's equations for this decomposition of the metric, the equations of motion for n and ni are not dynamical equations. They are not second time derivative equations. They are just constants. That's the structure of the Einstein's equations. And this Gij are the only part which is dynamical. So when you write down the Einstein's equations, the very fact that this n and ni are not dynamical leads to the fact that there are 2 constraints on the dynamics of these variables, which are usually called Hamiltonian and momentum constraints. This Pij is the momentum conjugate to this metric part, Gij. So these are very classic textbook stuff. Okay, so just to summarize, n and ni are not dynamical variables, and the fact that these are not dynamical leads to the fact that this h and pi are constraints. These are equations of motion for n and ni. Okay, so to summarize here, I didn't, oops. Give you the explicit expression of this h in terms of g and pi, and the same here. You can find it in the textbooks. For my discussion, the explicit form does not matter. Just the summary of this part is that basically starting from this form of metric, this is the dynamical variable, and this Gij and its time derivative, which I've denoted, essential time derivative, which I've denoted by pi, should satisfy these constraints. That's all. So you have a constraint system, and you need to study this constraint system. This is true for any gauge theory. Whenever you have a gauge system, for example, electromagnetism theory, or the gauge theories that were discussed earlier, are all in the same frame. So basically, some of the degrees of freedom that you start with are not dynamical, and there are constraints to be imposed because they are not dynamical. Okay. So now the question is, how do we quantize this system? It's a constraint system. To quantize this system, the usual way is that you promote this h and p, or Gij and Πij, into operators with canonical commutation relations, and impose these constraints, which are now some operators, on the physical states to be zero. That's the textbook stuff. For those of you who are familiar, this is called the Wheeler-de Wit equation. And this has been the basis for a field which is called quantum cosmology. So this is the standard textbook stuff. And basically it tells you that the Hamiltonian on any physical state, this is like a Schrödinger equation, but because in general relativity, there's a freedom in choice of time. This leads to something which is more like static type of equation, if you view it as a Schrödinger equation. Okay, but at the same time, this means that there is no preferred arrow of time. Okay, so far so good. This has been around for some good number of years. The point is that this sort of constraints are needed to assure the gauge invariance, here diffeomorphism invariance, or basically the manifestation of Einstein's equivalence principle at quantum level. So that's what the physical meaning of these constraints are. But the point is, if you try to quantize this constraint system in this way, there is no chance of getting arrow of time. So whether we can extend this in a way that we get an arrow of time is basically the ideas that we try to explore in these recent papers in a different context. But now I'm going to apply the same ideas to this system, GR and these constraints. So the point is that actually this diffeomorphism invariance of the theory does not tell you that H over any physical system should be zero. Basically, consistency of quantization requires this, where these OI are generic operators in the theory. So basically the endpoint function of any physical operator with H and Pi should be zero. That's what we get. And this is a weaker condition than this. Okay, so that's the main observation. This is more than what we need to guarantee gauge invariance or diffeomorphism invariance of the theory. Okay, so now recall the operator state correspondence, namely that any product of physical observables on the vacuum is a physical state. You can rewrite this in this form. So what we need to require is that sandwich of these constraints between any two physical states should be zero, not the right action. And this is a weaker condition than the right action. And this is what allows us to get an arrow of time. Okay, so that's the basic idea. As I said, let me repeat it again. This sandwich quantization conditions are actually what we need. And the right action is obviously if H on psi is zero, this is also zero. But to require this, H on psi need not be zero. These equations are defining what is the physical state. That's how to view it. And I'm going to solve this for you and show that it has solutions which are not H on psi equal to zero. That's obviously a solution. There are other solutions. Okay. So the idea to solve this is very simple, actually. Let's suppose that you have a Hermitian operator O, and you want to solve this sandwich condition. Let's suppose that this lambda is denoting the eigenstates of O, very simple, with eigenvalue lambda. And among these, there are zero eigenvalues, which are basically obviously satisfying this. But there are other solutions based on non-zero eigenvalues. Let's assume that this the spectrum of O has a Z2 symmetry, meaning that we have for every positive value of lambda, we have another eigenstate with minus lambda. And now consider this combination between positive and negative eigenstates with plus or minus sign here. And you can easily see that just by definition, O acting on lambda plus minus gives you a minus plus state, just by construction. Now, and plus minus states and minus plus states are orthogonal. So obviously, if I consider this combination, plus plus or minus minus sandwich states, this is zero, just by construction, because O changes this plus minus to minus plus. Okay? So you already see what's the idea of this, solving this sandwich conditions. If you restrict yourself only to a plus part or to a minus part of this combination, you basically throw out half of the eigenstates and restrict your Hilbert space to be consisting only a plus with plus sign here, you're already satisfying the constraint conditions. Okay, is it clear? So it's very simple. So now I didn't tell you what's the details of this H and P here in terms of G and pi ij, Gij and pi ij, but it doesn't matter, the details. What is important is that this H that we have takes positive or negative eigenvalues, and it has the symmetry that I used in this construction, this Z2 symmetry. That's all what is mattering. Okay, so now I choose my quantization scheme to be this one. As I said, I could impose either of them to be the right action or sandwich, but since I have not seen parity violation in my universe around me, this is the quantization scheme that I basically propose. For the momentum constraints, I still use the right action. For the Hamiltonian constraint, I use the sandwich. You could have done both sandwich conditions, but that's your choice. So I choose this to be my quantization scheme. And now I am basically going to solve this one, as I just mentioned. So this one, which is what you can find in the textbooks, is leading to a time symmetric class of solutions. This is time asymmetric, as I'll show you. And basically, this one has a solution which is like the right action, but has other solutions as I just constructed. And this is, again, some explicit review of what I just mentioned. Let's suppose that the eigenvalues of this H are denoted by epsilon with a sign, plus or minus. So this is the same eigenvalue equation that I had. Now I can construct plus and minus states the same way that I just did for a general example. The point is that if T is the time reversal operator, when it acts on this H, it basically gives me a minus sign when it commutes. That's just by construction. So if I choose now this class of plus states to be my physical Hilbert space, one can readily see that plus minus state goes to plus or minus this over time reversal. So this means that if I choose, for example, my Hilbert space to be consisting only on the plus sign, they will have a preferred direction of time. So this is basically the main idea. It's very explicit, very simple, very clear that when you want to quantize the theory at classical level, you don't see the arrow of time because you need to set H equal to 0. But when you come to quantum level, what you need to do is to basically set the sandwich of H equal to 0, which is not just H on any physical state equal to 0. You have this other class of solutions. And the proposal is that our universe is basically one of these non-zero eigenstates of H. And either the class that you choose, plus or minus, you have a preferred arrow of time. It's very simple. And this is very consistent with what we see around us, that basically the universe around us is not static. It's moving. It has been moving since the early time, and it has had a preferred arrow of time. So basically my proposal is that the Hilbert space of the universe that we see is actually state in my, for example, plus or minus set of states. Okay. So this naturally induces an arrow of time, and it basically tells us that you can never in the universe be in a static universe. It should always evolve, and that's what is called cosmology. So the solution has been there for the age of universe, but we didn't want to see it. Okay, so basically the proposal I have made is first of all giving the arrow of time in a quantization. So classical theory does not have arrow of time. It is within basically general relativity setup, which implies that all physical states that we have in any physical theory, because gravity is always there, there's always an arrow of time, and this induces arrows of time for every other system in the universe, whether it's a small thermodynamic system here or particle physics or whatever. So this basically simple proposal, because it's based on general relativity and this very simple quantization scheme, is going to solve the arrow of time problem. It not only tells you that why there's an arrow of time, it also tells you why these three different arrows of time are always pointing in the same direction. Okay, so these are some, just to basically show you a figure, that all states that I had in my Hilbert space, half of them, which are in this physical part, the other half, in my case, epsilon minus type states, are in the complement part. If you are in the physical part, the time direction flows up. If you are on the other part, then time direction flows down. But this is the physical part of the Hilbert space that any observer has access to. So either you're here or there. You cannot move between them. That's just by construction. Okay. So probably I already told you about this. As I mentioned, this is also just as a final comment. Quantization, it has always been something like a black box. You start with a classical theory, you basically push it through this black box, which is called quantization, and you get some quantum theory. And basically, we don't start from a quantum theory and take a limit and then obtain classical things. So this is something bothering. And I think if we have a final, more fundamental theory, this should not happen, that quantization should not have any meaning. You should just directly start from quantum theory. But that we are not there yet. So in this black box, you may have some freedom to play with. And I've tried to use that freedom that we had in the context of a system which has a constraint. That was general relativity in my example. And I chose my scheme to be, for example, sandwich condition for one of the constraints and the right action for the other. If I had basically started from this, this would have led to this quantization scheme would have led to a universe which allows for parity violation at cosmic scales. We have not seen this, or we are not sure if we have seen parity violation at cosmic scales, but that option is still open. You are free to choose this quantization condition rather than what I showed here, which was right action for P and sandwich for H. Okay. But there are some hints of parity violation at cosmic scales, and maybe we can think about this one as well. Thank you for your attention.
Thank you. Thank you very much. Questions? Actually, while waiting for some possible...
Suppose you have two universes with different eigenvalues for the time reversal operator. Unless you compare them, can you distinguish between the eigenvalue, like in the individual universes?
Mm-hmm. Okay, so let me. So you're saying that somebody lives in this part of the universe and somebody else would
right. And yeah,
any connection between the two would break diffeomorphism invariance.
Right. Unless they talk to each other, so yes, they cannot tell.
If they talk to each other, this means breakdown of general relativity.
Yeah.
That's what I didn't explore, but that's possible, of course.
Okay.
I have a short question. You have these two pieces, and your result sounds like Wigner's theorem. No, unitary, anti-unitary transformations, either this or that. Can you comment about the possibility of entanglement between matter and antimatter? That's electron here, positron here, plus positron here, electron here, divided by square root 2. Why is it impossible, or what do you say?
That's a very good question. Here I told you about one specific example of the sandwich quantization, but it was just one example. It appears in any system when you have a constraint in the system, in any gauge theory, or actually you mentioned one other example. Let's suppose that this symmetry that I want to find the sandwich between is CPT. Okay, so I can impose CPT, that was the example you mentioned, on physical states, on the physical inverse space to be sandwiched between CPT operator to be 0. And so that is a good quantization scheme. And I can basically, if I start with this and try to quantize it, this means that for every CPT, positive state, I need to have a combination with CPT negative. So this basically tells me that the vacuum state that I choose here is breaking CPT maximally. So it only allows for example, CPT odd or even states. So that's not what we have seen in nature, or we think we have not seen. So